Okay. Okay. So today we don't have many people here. The first question was how do we write filter using fold? How do we do that? Somebody?
So one of the arguments to the fold function would be a lambda function that takes two arguments, x and y. And
Yeah.
if x satisfies the predicate condition of the filter, you const it with y, or else you just send back y.
Okay. Very good. So the filter has the following syntax: filter, predicate, and list. Yeah. This is the syntax of filter.
Sir, your screen is not visible.
Ah. Yeah, so filter has this following syntax: filter, predicate, and list. Predicate is a function. Predicate is a function which takes a list and gives you back a boolean. Yeah, this is the it takes a list of some type A and then gives you back a bool. And list is some type A, which means that it's like box int or box. Box here means list. A means some type variable. It could be int, it could be string, but it's the same type. Yeah. So these are the two things. Paran, any question? Okay. Now, so how do we write? So we write fold has the following syntax: fold. Let's write fold R, then function, func, value, and list. So now, if I want to write filter in terms of fold, I'll say fold filter is equal to, and just fold of, then I just need to have a function lambda, and that function takes two arguments x and y, and if the predicate is true on x, on let's imagine it is yeah, is true on x, then it returns it. What does it do? The predicate is true on x.
Sir, cons of x and y.
Cons of x and y. Otherwise, it just returns y. Why does it? Oh, and the other arguments to fold will be, what should be the value? Value is just the empty list nil, and then yeah. So let's write it like this: filter predicate list is nothing but list. Yeah, this is what it is. Filter predicate list is nothing but fold of lambda xy. If predicate x, then you cons xy, otherwise you just return y, and nil and list. Okay, so that was the first question. What is the second question? What are the constituents of a data abstraction? So somebody tell me what are the elements of a data abstraction? What do we mean by a data abstraction? What are the things?
Sir, the constituents are a constructor,
Yeah,
the selectors or accessors,
yeah.
the contract between the constructor and the selectors, and
Okay.
a predicate to test whether some data is of the type of that
All
abstract.
right, perfect. So it's four elements: the constructor functions, the selector functions, the contract between them, and the predicates for testing them. Perfect. Now the last question was, yeah, what is the use of tags? How do we use tags? Why do we use tags? Or where do we use tags? Yeah. Somebody? Where do we use tags?
Sir, when we have a function dealing with the like it is a module which is dealing with different types of data as input, so we can just tag the data and classify them, like use them accordingly, use the data accordingly.
Yeah, that is one place where you can use that. Whenever you have different data representations, to distinguish between them, you can use tags. That's one answer. And but in the last lecture, there was another thing called defensive programming. Does anybody remember what is defensive programming?
So it's used so that we can flag an error in case there's an input we are not expecting. So the tags allow us to keep track of that and prevent us from putting out outputs that don't make sense.
Yeah, exactly. So the point in the idea of defensive programming is that whenever you program, you expect nonsense to come in as input. Yeah. And so instead of taking that, okay, I will only get good argument, I will only get valid inputs, you always expect you will get bad arguments. And so the tags come in. The tags help us to format, to check if the coming arguments is in valid form. So that's the idea of defensive programming. Okay. All right. So those are the two places where you can use, but I just asked one use. So if you give one use, I'll give full marks. Okay. All right. So so today I didn't ask you to watch any video. So let's try to do some examples from, let's try to do two things. One we mentioned in the last class, but we didn't finish. The one was 8 queens. Anyone use, program 8 queens? I don't think so. Okay. So what is 8 queens problem? It's 8 queens problem. So let's try to do both of them. One is 8 queens and the other is knights tour. Okay, so what is 8 queens? So everybody knows what is a chessboard. Yeah, a chessboard has 8 by 8. It's usually 8 by 8. The Jama chessboard is 8 by 8. Now, so to address the cells of the chessboard, you can use in the modern chess. They use something called algebraic notation. They call the rows they call as files, no, as ranks, and columns they call as files. And the rows are labeled as 1, 2, 3, 4 up to 8, and the columns are labeled from A to H, A, B, C, D, E, F, G, H. Okay, so the bottom leftmost corner will be A1, the top rightmost corner will be H8, and so on. That is how in modern chess notation you will indicate moves. For instance, the move of a pawn from in front of the white's king 2 steps forward will be E4. Yeah, so that's how it will be. But for convenience in our programming, we can just use as an array, chessboard as an array. So the bottom leftmost corner will be 1, 1, topmost right corner will be 8, 8, and the A8 will be what square? The first column, last row element, the leftmost top corner will be le will be what? Will have It will be 8 comma 1. Yeah, 8 will be the row and 1 will be the rank. 1 will be the no, it will be, yeah, it will be 8 1. The first column, 8th row. Yeah, okay. So now that is how we will address the chessboard. Yeah, 1 1 to 8 8. Now 8 queens puzzle is this. So if I place a queen, queen is what we call mantri or bishop. No, mantri in Hindi, I think. Yeah, is it mantri?
But I think it's Wazir.
Ah, wazir. Okay. Yeah. So queen is the most powerful piece on the chessboard. Usually it has value 10. So whenever you place it on a square, it will control the row which contains it, the column which contains it, and all the diagonals which contains it. Yeah. So if I place the queen on 1 1 square 1 1, then it will control the first column, and it will also control the first row, and it will control the diagonal 1 1 2 2 3 3 4 4 up to 8 8. Yeah, it will control those diagonals. Now my problem is I have 8 queens, and I have to place 8 queens on a chessboard in such a way that no queen attacks the other. Yeah, they are not in conflict. You understand what I'm saying? For instance, if I place a queen on 1 1, and if I place a queen on 2 2, they are in conflict because they are controlling the same diagonal. But if I place one queen on 1 1, the other queen on let's say 2 3, then they are not in conflict because they are not controlling any common lines, any common diagonals or rows or diagonals. Yeah. So the problem is we have to find a placement of 8 queens on a chessboard. That is the first problem. Okay. All right. So let's try to do the first one. Can you try to do the first one, 8 queens? It's a, so how do we program this? How do we check this? Jarrett? Hello? Is it stuck? Nobody's answering.
No, sir, it's on.
Sir, you are audible to me.
Yeah. Yeah. So who are you trying already? Please try it. It's not a big problem. But somebody can tell me the idea. How do we check if we can place 8 queens on a chessboard? What is my idea? What is anybody's idea? Tell me.
So from 1 to k minus 1, all the queens are placed. Then the kth queen appears in a new column. And then you have to just check it that she does not sit on any other diagonal that matches with the previous queens. And
Yeah.
you incrementally build the board.
Yeah. So this idea is called backtracking. Okay. So the point is that how do we, well, let's try to formulate the problem in terms of our data structures. So we have a partial assignment of the placement. Yeah, partial assignment, partial placement of the queens. How do we do that? A partial placement of the queens will be a list of pairs of the form xy. Yeah. So for instance, if I have a list which says 1 1 2 3, this is already placement of 2 queens. Yeah, one queen on 1 1 and the other queen on 2 3. Yeah. And so how the point is that I will start initially, I will start with we will start with empty list, and we will we can enumerate all the cells from 11 to 88 that are not in conflict with the placements so far, and extend the list. Yeah, get it? Does anybody understand what I mean? Hello.
Yes, sir.
All right. So can you try to do this problem? Is anybody trying? First of all, is anybody trying?
Yes, sir, we'll try.
Yes, sir. I
Yeah.
have started.
Yeah. Let's try, and maybe, yeah. Everybody try. Maybe Saina, are you trying?
Yeah. No, yeah. I start.
Okay. Just think about how will you do this, and maybe 2 minutes later we can discuss, or 5 minutes later we can discuss how you are trying to do this.
Sir.
Yeah.
Sir, I encounter this problem while thinking in this language that it doesn't come naturally. Like I tend to think in C or Python, but like then I get confused while translating to this.
Mm-hmm. But the point is that when I was a bachelor student, these problems were given as part of our Lisp coding, and for that time for us this was, I mean, these problems are backtracking problems are more natural in Lisp. You understand what I'm saying? Because you have these problems are naturally recursive. You agree with that? How do we see the point? How does backtracking work? So the point is that you have a partial list. You take a next element. Okay. Now that next element is just a guess. It's a guess. Now that guess is based on you take a guess by enumerating all the possible cells, and you take a cell and check if it is in conflict with the already existing assignment. If it is not in an existing assignment, you add it to the list, and then you extend the list, and then you recursively go deeper. Okay. Now when it doesn't work, when you come back, you will naturally extend the next list, consider the next element, and go. Are you getting what I'm saying?
Yes, sir.
Okay, so somebody tell, I'd like to see the progress. Hello. Who can show me some? Anushri? Who is Anushri?
Yes, sir.
Can
Sir,
you
I'm
show me
trying.
can you show me what you're thinking?
Sir, we'll define the function with two arguments, the initial list and the access. And if the char of the initial list clashes with the access, then we are changing the position next. We are changing to next position. Otherwise, we will again call the function list of then the function ladder of initial list and access.
Not very clear to me what you're trying to do. Devansh, Rajnish is here. Rajnish. Hello.
Hello,
Yeah, who is this?
Sir
Saina?
Devyani.
Devyani, yeah.
So I wrote the function where we place a new queen on the board given the old board, and
Yeah.
now all I have to do is put it inside a lambda enumerate or map function that keeps adding a row to it.
Okay, show me. Show me your code. 1 second, I'll show. Yeah. Yeah, show me.
So it's still disabled.
Yeah, it is enabled now. Okay. Yeah. Define new keyboard colon n.
N is the size of the chessboard. Column is the
Okay.
new column in which I want to add the queen.
Okay.
Then iter function will check have you already checked for all rows? So that's greater than n. Then I'll just send back the board I've already had.
Yeah, if the row is what is this row is row greater than n new board?
So that means that I've already checked all the rows for possible positions of the queen.
Okay, you are enumerating from 1 to n.
Yes, sir.
Okay.
Here I'm checking if the queen lies on the diagonal. So I do that by checking column minus column and row minus row shouldn't be equal, because if it is, then they are on the same diagonal.
Yeah.
If that is the case, then select a new row position.
Yeah.
Plus
Yeah.
row
So,
one.
but you should avoid doing this line. Instead, you should write a separate function, conflict or something like that. Conflict
Yes,
with
sir.
with a question mark. Okay.
Okay, sir.
And but you are not representing it as a list internally, are you?
So list of tuples. Yes, sir.
Which is the board.
Yes, sir.
Okay. Care of board. Yeah. It's.
And if
Yeah. I understand what
there
it
is
is. Yeah.
yeah.
Yeah, but the point is that this way, nobody will be able to understand
Yes, sir.
what is the logic. Yeah, so you should try. That is the whole point we were doing with this data abstraction thing.
Yes, sir.
How to split it into understandable pieces. Okay, so this you got it. This what is this new queue?
Sorry, sir.
What is this new queue with this board? You are checking if it is conflicting. What is it?
So I'm asking for a new position of a queen in the 6th column.
Okay, 6th column. And what does it return?
6, 1 along with the old queens.
Okay, so it is just added that. Okay.
Yes, sir.
All right. Okay. Can you redo that whole code in terms of understandable pieces?
Yes, sir. I'll
Use
just-
use abstractions like use position for a pair. Okay, pair XY, and use board as a list of positions, and so on.
Okay, sir.
Yeah.
Yes, sir.
Yeah. All right. Somebody else. Somebody else. Sir, can we start from placing all queens in a single column and then keep moving to the right side to avoid conflicts? I don't know how that helps, because essentially this is a backtracking algorithm. Backtracking algorithm in the following sense: you start with a empty list, you add a tuple, you add a pair, okay, a position into that list, and then you check if all queens can be placed with that pair. I mean, that list can be extended. So how do you check that? You add another position and then check if that can be extended, then you add another position. So the list goes to 1, 2, 3, 4 up to, let's say, 6, length 6, and then you find out that okay, there is no way you can extend this current configuration. So then you have to backtrack. You have to come to the previous recursive step and try the next position, and so on. Okay. Now, why you will see, perhaps it is not very clear why it is the case that you have to backtrack with the current 8 queens puzzle, but in the next night's tour, we will certainly see you will have to backtrack.
Pawn e7 to e6. Pawn c7 to c5.
Okay, everybody just concentrate for 1 minute. Let's quickly understand the knight's tour also. Okay. Hello. Hello.
Yes, sir.
Yeah. So what is knight's tour? So there are, this is what I was saying. This is A1, this is A8. And but we will represent this as 1 1, 1 2, 1 3, etc. And this
Sir,
will be
your
2.
screen isn't visible. Like
Yeah. Yeah, so this is a chessboard, okay? And this is a knight. Yeah, this is a knight. Now, which all position this knight can jump? Can you tell me the positions where this knight can jump?
sir, G1, G5, and E5.
G1. This, damn it.
Knight b8 to c6.
So yeah, this move. Let's
Knight c6 to b8.
yeah. So this one can jump to G1. Then ideally this can go to this position, then this position, and this position. Yeah, this will be H4. This will be G5. Then what are the other places you said, Siddharth?
Sir, E5 and
E5,
D4.
D4, D4. Yeah, and it cannot go to D2 and D1 because those are all occupied. Yeah, so ideally the knight's positions are three cells, but either with 3 cells with a turn. So I can go like this and this, or I can go like this and this. Similarly here, or here, or here, or here, or here, or here. Yeah. So ideally, if a knight is placed in a cell, it can go to at most 8 cells. Yeah, 2 here, 2 here, 2 here, and 2 here. At most 8 cells. But it may not be able to go to all the 8 cells. Okay. Okay. So knights. So if a knight is placed in, let's say, XY, what are the positions where it can go? So that you will be able to find out. Yeah, it can go to from XY itself. You will be able to tell which all positions it can go. For instance, it can go to X plus 2 and Y plus 1. That's one position where it can go. And similarly, there are other positions where it can go. Okay. Now, what is knight's tour? Knight's tour is you are given an empty chessboard and you are given a position where a knight is placed. Like in this case, it is placed in F3. Okay, or 3-3 in our notation, 3-3. So the knight's tour problem will take an empty chessboard and a position like 3-3. And what this function has to output is this knight has to traverse through all the 64 cells of this chessboard, all the 64 cells, but exactly once. Okay, so it cannot jump into a cell where it has already jumped into. So it can only once jump into exactly once to a cell. Okay, and that way it has to complete the entire chessboard. Now it is not possible to so if you're so yeah, so any that's the question. Now a knight has to start at a particular position with the given position, and it has to check if it is possible to traverse the entire chessboard visiting every cell exactly once. Now there is a different name for visiting every node of a graph, every vertex of a graph exactly once. What is it called? If I am given a graph and if I visit every vertex exactly once, such a tour is called a,
Euler's tour.
It's an MO clock.
Traveling.
pardon? Euler's tour is when you visit every edge exactly once. Okay, but you don't. But if you have one vertex has many edges,
Traveling
going,
salesman problem.
yeah, it is traveling salesman problem. But such a path is called Hamiltonian path.
Hamiltonian,
Okay, okay, it's after, yeah, it's named after its originator. So Hamiltonian path means that you are given a graph. You start at one vertex of the graph, and if you have a path which visit every vertex exactly once, then it is called a Hamiltonian path. Moreover, if you start at a vertex and finish at the same vertex, it's called a Hamiltonian cycle. Yeah, it's a path, it's a cycle in the graph which visits every vertex exactly once. Euler tour is coming from Euler's problem of the
Königsberg bridges.
yeah, Königsberg bridge problem, where you have 7 bridges and you have to traverse every bridge exactly once and come back to the same place. And the question is whether it is possible or not. Yeah, so that is called Euler path or Euler cycle, visiting every path exactly once, every edge exactly once. Now, these two problems, even though it looks very close together, they have different complexities. Euler path is solvable in polynomial time. You're given a graph. To check if it has Euler path, you can, there is a very simple thing we have to check. You have to check that, every the odd number vertices, the odd degree vertices are odd. That's all you have to check. Okay, and the graph is connected. That's all you have to check. So that is polynomial. But checking if a graph has a Hamiltonian path or a Hamiltonian cycle is an NP complete problem. That means that so far we don't have anything less than an exponential solution, exponential time solution. Yeah, the best we know so far is exponential time solutions. Okay, so that is how you have. So that is a problem of Knight's tour. Knight's tour is actually finding. So if you this, how do we formulate this Knight's tour problem as a graph problem? What are the vertices and what are the edges?
Sir, all the positions are the vertices, and
Vertices,
all the
yeah.
8 jumps that the knight can make in one position are the edges from
Are the edges, exactly. So for instance, 3 3 will be a vertex. 3 3 will be a vertex, and it will have an edge to 4 and 5. 4 5 3 3 to 4 5. There will be a path. There will be an edge, and similarly there will be an edge to no, this is not 3 3. Sorry, this was 6 3. Yeah, it's F3, so it's 6 3, and 6 3 to 7 5 there will be an edge. 6 3 to 8 4 there will be a jump. So 6 3 there will be an edge to 7 5 as well as 8 4 as well as these other vertices also there will be. So you can actually see this Knight's tour as a Hamiltonian type path problem. Yeah, but to solve our problem, we don't need to see this as a graph problem. You can see this as a so how are we going to solve this problem? Give me a strategy. Hello. So the point is that you start with a singleton list which contains a starting position, and then you have a function which gives you adjacents, the possible positions a knight can jump from a position, and then you take the last element of the list, find out all its adjacent positions, pick one. So the adjacent pick the first element of that list, add it to the current list, and then call that function recursively so that knight will jump there. Now, if knight cannot jump into any position, then that recursive call will end. You will come back, you will find the next position and jump there, and so on. Okay, that is the strategy. That's called backtracking. You come back and then you try the next position and then you jump there. Okay, and yeah. Now yeah. Any questions? Any questions? All right. So can you do these two problems as homework? These are very important problems because they give you a good idea about recursion and backtracking. And let me give you one. It is not possible to speed up Nightstore because as I already told you, Nightstore is a difficult problem because it's actually computing a Hamiltonian path and it's an NP complete problem. Okay. Now, but it is possible to speed up your Nightstore. Okay. So, for instance, there is a practical speed up, but not theoretical speed up are called heuristics. Okay. For instance, if a knight is sitting here, then the idea is that the knight should first jump into the you look like this in the initial phases of my Nightstore. If my knight is, imagine my knight is placed here, where should it jump? I could actually jump it here or 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 here. All the 8 positions I could jump it to. But I could actually say that, okay, why don't we jump it to the edge, the positions which are closest to the edges of the chessboard. Why? Because the positions which are closest to the edge of the chessboard have lesser number of positions which are adjacent to that. So therefore, I would like my knights to visit the outermost positions first before it goes into the inner positions, because inner positions I have always more options to jump. Yeah, but outer positions don't have that many options to where I can jump. So therefore, I would like in the initial phases, whenever I am given an option to jump into a position which are closest to the rim of the chessboard, I would prefer that than jumping into the inside of the board. That is a heuristic, because you will see that once you program this Nightstore, you will find that without this heuristic, first you code without any heuristic. Okay, just you code it without thinking about anything. Just try to find a Nightstore, and then you apply the Nightstore. Then you will see that your program will finish fast. Okay. Any questions? Hello. All right. So for Tuesday, can you do these two things and come? Also, can you watch the lecture 11?
Yes, sir.
Yeah. So advanced data types, lecture 11. And you do these two exercises also. Okay. So somebody please do it, and please post your solutions. And when you do, keep in mind that you have to write your code in such a way that it is easily understandable for others. So just don't use all don't strictly have a separation between your internal representation and your program logic. Yeah, you can use you are going to use list as your first saving the tour so far, but then don't use just use car and cutter. Use meaningful names. Yeah. All right. Okay, then you can continue. I'll stay here till anybody. Any questions? Any questions? Jarrett? I don't know. Okay, then. See you on Wednesday. And please do this thing yourself. Okay, even please do this both this nights tour and this one. I will personally ask you to explain your code. Okay. Yeah. So in the next class, you can. I will ask people to. When if you are finished, I will ask you to show me your code and we will discuss. All right.
Okay, sir.
All right. Thank you. Bye.
Thank you,
Thank you,
sir.
sir.
Yeah. Bye.